Okay, thank you very much for this kind of invitation. So it's really a pleasure to talk about my work with Hubert, who I knew well, and actually we really started knowing each other doing this work together. So this had certainly a big influence on my career, because I was doing small calculation in my side and a bit hidden in my office, and Hubert came and told me, well, we should really work on that, and we wrote, I think, a nice paper. So I will talk, well, I mean, so let's say, so this is the title, and this is not the same picture, but this is also a picture of Cézanne. So okay, it's not so far from what we are discussing today. So I mean, this paper started really well. I started to know Hubert with this work, and I must confess I have been working on this subject nearly all the rest of my career. So certainly this had quite a big influence on me. So what was it about at that time? So we were considering an open XXZ chain. So maybe Jean-Bernard Hubert told you a little about at the beginning of this conference, and we were putting this boundary term. So why did we put this boundary term at the end? I mean, actually, it's not very difficult to understand why we did that, because we were interested in the subject of the Temperley and Lieb algebras. So, and Temperley and Lieb algebra, it had to do with models known as a restricted solid-on-solid model. And this restricted solid-on-solid model, as you know, that they somehow get cut at some end. So all the, I mean, you would think that all the possible representations of SU2 would appear in the restricted solid-on-solid model, but somehow after a certain while, they disappear. So we wanted to understand, and the restricted solid-on-solid model, we knew that they were connected to the XXZ chain. So we want, the reason for that is that the Hamiltonian of both models can be just written as the sum of Temperley and Lieb generators. So we really wanted to understand this connection. So then we looked at the somehow. So we were just taking tensor product of spin 1/2 representations, and we were looking at how the generators of SL2 or QSL2 act, and because so you see, I mean, we had this kind of picture, and the thing that is a bit striking is that so normally you would expect for ordinary SL2 that you have just tensor products is 3/2. So if you tensor three spin 1/2 spin, you find a spin 3/2 and 2 spin 1/2. But what you observe in that case is that the spin 3/2 gets coupled to one of the spin 1/2 representation, and some of the arrows in the spin 3/2 disappear. So, for example, if you act 3 times with S minus, you don't find this state. I mean, after 2 times, the third time it gives 0, and the same with S plus. So I mean, well, that was intriguing, and that's what we kind of developed in this paper. But what I will talk more about in today is the fact that you can somehow discover new generators which are taken by some limit of the SU2Q generators, and these new generators, they really couple the 2 states up and down, and moreover they have the property that they obey an ordinary SL2 algebra. So it's not no more SL2Q, but somehow hidden into SL2Q there is an ordinary SL2. So far so good. So now, well, although with Hubert we looked at the closed chain, quite a lot, but somehow the observations that I will make today are a bit disconnected of what we did together, or maybe it's not disconnected, but then maybe Hubert will tell me about that. And so the work I will discuss today was done with Jules Lammers and Yuan Miao. By the way, I should say that Yuan is a very bright student. I really enjoyed very much working with him, and I was told that he's still looking for some jobs. So if some of you, I mean, this is my recommendation. I think if you have the opportunity to give him a job, that would be very, very good. Okay, so now, I mean, this is just the ordinary closed spin chain when Q is a root of unity, and somehow, I mean, then it does not commute anymore with the quantum group, so you think it's going to be a bit messy, but so there was a work by Fabricius and McCoy a few years ago, and they really discovered something which I find quite interesting. They find that there is now a symmetry not on SL2, but of the loop algebra of SL2. And so, well, this is hacked. So they could find the generators. It's a bit complicated, and I don't want, because, well, I mean, actually, I don't think they find them in all the cases. So this is still something a bit confusing, this SL2 hat algebra, but nevertheless, they discovered interesting phenomena. And in particular, well, so somehow you have to study the representation theory of the loop algebra, not the Q loop algebra. This is a Q-deformed model, but we've just again find the ordinary SL2 loop algebra hidden in that. And these finite dimensional representations are kind of a tensor product. I mean, that this is the theory, irreducible representation of SL2 loop algebra are simply tensor product of what is called evaluation representation. And these evaluation representation are just, so it's just a tensor product of, if you want, n spin 1/2 representation. But since you have this, in the loop algebra, you have this spectral parameter, which is z. You have an n in a tensor product of n of them, n numbers, which I call ai. And it's quite natural to introduce, so it's called the Drinfeld polynomial of the representation, and it takes the form a product of z minus ei. And the roots of this polynomial are just the evaluation parameter. So I think what remained a bit mysterious today, up to now, although there was some work by Fabricius, McCoy, and Deguchi and other people, is a bit where are these ai hidden in the spin chain. So I will discuss this a little more. By the way, also in this work, Jean-Sébastien Coe was involved. Actually, he was the one who proposed me to work on this subject, but probably maybe he didn't like it, so at the end he disappeared. He said he didn't want to be on the paper. But okay, I should thank him a lot, because I wouldn't have worked on that without him. So now to have another point of view on this model, you have to look at it from the point of view of a 6-vertex model. I think this is more interesting. So, well, here I describe what is the 6-vertex model. You have 6 weights, and they have this famous weight A prime, BB prime, CC prime, and well, I mean, here I put A square, but it's A prime. You have this quantity which is related to this parameter delta of the XXZ Hamiltonian. So, and this is well known forever, that the transfer matrix which you obtain with which you construct with the 6-vertex model commutes with the Hamiltonian. But here I would like just, I mean, for those who are not expert, I would like to introduce what I call the Sklianin 6-vertex model. But it's a very well, it was a very beautiful idea at the time, but due to Sklianin, that you can somehow take your Lax matrix. So what is the Lax? Well, maybe later I should go. So, well, I mean, what I would like to say here, that you want to mix something which has a spin 1/2 in one direction and another representation of the algebra on the other direction. So 6-vertex model was just when you had 2 spin 1/2 on both links, but now I have a kind of a larger spin representation on the link. So that was the idea. The idea was to write the kind of RLL equation, and then instead of putting the weights of the 6-vertex model into the L matrix, try to find some new operators. And actually, what was discovered at the time is when you put these new operators, you discover an algebra coming out from the RLL relation, which is this algebra, and this is called the quantum SL2. So I will use this kind of framework to understand what happens at root of unity. But maybe something I would like to say, but maybe it's not going to be completely obvious, but somehow Paul Findlay, for example, he introduced a model where you build a big transfer matrix going in this direction, so many red lines and just one black line. So the black line is called internal space or auxiliary space, and the red line is called physical space, I mean, in the jargon of... but here I will use this thing in just the reverse direction. So I will use... So although I think it's quite connected to Paul's talk, the red line will be my internal space, and so the black lines will be my physical space. So it's still spin 1/2, tensor product of spin 1/2 representation. So I'll tell you why I have to introduce such an object. No, now I change a bit topic, and I would like to explain to you what is the idea behind the work of Fabricius and McCoy. So just, when you solve these models, you always encounter this kind of equation, which are called Bethe equations. So I do not have time to explain how they arise, but anyway, you have to solve such a set of equations, and in a given magnetization sector, if you want the magnetization sector tells you how many spins you reverse, you have to find a kind of set of rapidities, m of them, which for any state, for any eigenstate of your Hamiltonian or transfer matrix, which obey this kind of equation. Now what happens, I said I would, so I said Q was something like exponential I eta. So what happens when this number L eta is a multiple of pi, so in this kind of special root of unity. So eta is some pi over L, if you want, I pi over L. Then you can consider such a factor, sinh u minus alpha, sinh u minus alpha minus eta, minus L minus 1 eta. And then suppose you have this is something like q of u minus eta, um minus eta divided by q of um plus eta. You multiply your q by such a factor, so you set u equal um in this product, and plug it in here, and it doesn't change at all the equation. They are just exactly the same equation. So somehow it seems to me that whenever you have one solution of the Bethe equation, you get another one by just multiplying by such a factor. So it seems that you will have degeneracies between states exactly like we had in the first transparency, which differ by a magnetization of L. But of course, this is not true. So, but this is not true in general, but this can occur. So the question is, when does it occur? And can we somehow assess a little more about this? So this, whenever you have such of a set of rapidities, say you have so say um. So now you have a rapidity which is alpha plus eta, alpha plus L minus 1 eta, and eta now is purely imaginary. I should have said it. Normally they should have put an I here. This is called the string. And in our case, we have what is called the complete string, because we have exactly L Bethe rapidities along the string. And it is also called an exact string, because, it's completely exact. So let us ask a few questions then about what happens in that case. So one of the questions is when such factors occur in the spins, there are degenerate states with magnetization differing by L. So when does that occur? If it occurs. As I tell you, the center of the string is this quantity alpha. So I already answered the question. Does the eigenstate depend on alpha? In fact, it turns out that it does not depend on alpha. So why should we care about alpha? Does alpha has any physical meaning? So alpha is called the center of the string. So let's try to somehow put a little light on those questions. So now that's why I wanted to introduce this kind of transfer matrix. So whenever you have a kind of any representation of your SL2 algebra, you can put an internal space with it, and you can construct, well, what is the transfer matrix? It's just the product of this L matrix, these L operators I introduced. But now you don't multiply them as 2 by 2 matrices, but you multiply them as L by L matrices. So just you reverse you turn your head 90 degrees if you want. And whenever this occurs, this matrix commutes with this matrix. So this gives you a kind of symmetries, if you want, symmetric operators. So that's a way to look at the conserved charge in your system. So I will try to use this a lot. So I mean, now why do the transfer matrix commute? Because you have this so-called, well, I mean, I can go here, the so-called Young-Baxter equation, which is this equation, RLI equal L prime LR. And in that case, where you have 2 black lines and 1 red line, you don't have to care too much about what the red line is. I mean, they always commute, just because you have 2 black lines. Now you would have a more subtle case where you would have 2 red lines and 1 black line, which I will discuss a little later, and then it's a little more subtle. Because why in that case, the R matrix is just the black R matrix, which is just the R matrix which you knew from forever. So now what kind of red line representation will I use to understand these special beta roots? Let us call them Fabricius-McCoy beta roots. Well, again, it's kind of special representation that occurs at root of unity and only at root of unity. So you see, I have my kind of representation. As I would do for SL2, it's always possible to have a kind of lowest state, which is annihilated by S minus. So now I have my lowest state, and it's annihilated by S minus. So I can construct my representation. But now what is very special about these representations is that because it's a root of unity, I am also ensured, just by periodicity, that the state L will be also annihilated by S minus. And whatever the parameters, whatever the spin is, J. So this spin J could be usually you have to take, if you want to find finite dimensional representation, you have to take J to take half integer values. But in that case, you can take any value you like because of this property that S minus will annihilate L, and you still find a L dimensional representation. And this is special to root of unity case. So actually my red line will be in this representation. So now let me try, I see jump to something, try to see why I find this problem a little interesting, and I try to give you some kind of physical motivation why actually I did not study this problem because of physical motivation. I studied it because Jean-Sébastien had called me and asked me to work on it. But nevertheless, there is some physical motivation. And so this comes back, I think, for some old work, well, first by Thomas Prosen, and then Pereira, Cirker, Affleck, and myself. And the motivation, which is also something interesting, is the current in the spin chain. So you imagine that you have a quantum spin chain. So your particles are your spin down, if you want. Your spin up are just like holes, and then you create some current in the system. And it turns out that when Q is a root of unity, you have some kind of a persistent current that remains all the time in the chain, even at infinite temperature. So here we were interested in the infinite temperature case. And to study this current, why this current remained, we were relying on, actually the idea comes from Thomas, from this Mazur bond idea that is it possible to find some kind of charge such that when you compute, well, here the expectation value of the current square divided by, properly normalized. This gives you a lower bound to the say current time correlation function, and that's what we are interested in. This kind of recurrent current is obtained just by computing this limit. And so how to construct such charge? It's not completely obvious, because the usual charge you would construct, they are invariant under reversal of the chain. So when you compute their expectation value with the current, it gives 0, because the current is odd under reversal and the charge is even. So we had to construct such charge that are odd, and actually that's really by considering this special representation with which I just presented, that you can construct such current. And then, I show you the kind of bound which was obtained, and the result of it is quite striking, because you obtained Drude weight which has a kind of fractal behavior. So for any root of unity which is to the power which is a fraction, if you want, q exponential I times a fraction, you find kind of a discontinuous. So there you kind of find a kind of lower curve for the irrationals, and then kind of discontinuous. Now there are two curves. I don't remember where they come from, but anyway, the important point is that you find such discontinuities. So it's a bit. There was a talk by. Well, I will talk, but think of the talk given by Boulat yesterday. So he was saying that you were finding something continuous. So in that case, it's just the contrary. You find something extremely discontinuous, and I think this might be of some interest. Maybe I had something else to say about this. Okay, no, let's go. So now I have a. So now maybe let me come back to the more mathematical motivation. The mathematical motivation is a bit more to understand this so-called action of this SL2 hat algebra into the spin chain. Maybe since Paul is here, I could say that there is hidden in the SL2 hat algebra, there is something called Onsager algebra. So maybe this is also a motivation to try to understand connection with Onsager algebra. Yuan would have more to say than me about that. But at this stage, but maybe I won't say much about that. But anyway, it's a motivation. So that's about the degeneracies I was talking about. So you study a spin chain of length 12 at root of unity exponential I 2 pi over 3. And you see there are really, so you have many degenerate states at m equals, so multiple of L is 3. In that case, you find the degenerate state at m equals 0, 3, 6, 9, 12. And well, here I have put these roots, alphas, which I was discussing. So maybe something, yes, which is interesting. You see that whenever you have well, here you do not expect to see degeneracies, but here you would expect to see. So here you have 4 degenerate states, and that's why somehow alpha has not really much meaning about the spectrum, because if you change alpha, if you change your definition of alpha, the only thing that you will do is you mix these states together. So you don't really, alpha seems to have no role to play to understand the degeneracies of the spectrum. You could take any alpha you find, at any alpha in your eigenstate, so you write the eigenstate corresponding to the beta solution, and you just find linear combination of eigenstates. So maybe you think this alpha has no meaning, but still I want to convince you that it has some meaning. Maybe also something which is interesting is that this has to do with this SL2 hat representation. This has actually a dimension 2 to the power 4. 1, 2, 3, 4. So it is kind of consistent with the tensor product of SL2 of spin 1/2 representation of SL2 hat. So I'll try to explain this a little better. So now. Well, this is also has to do with Edgar Boulat talk. Well, you see, I was talking about strings. So the strings, somehow when you're in the ferromagnetic sector of the spin chain, they are very easy to understand. A string is just a bound state of spin down. But in this region where Q is the root of unity, I think they are very mysterious, and we don't really understand what they are. So somehow in the TBA was performed by Takahashi many years ago, and he had the classification of strings which work for roots of unity, and so you had to take your Q is this root of unity, exponential 2 pi I 13/16, and you make a continuous fraction decomposition of your state, and then you discovered that you have a kind of 8 strings, and somehow only well, you have 8 strings in your spectrum, and well, I mean maybe it's going to be the next transparency. Okay, and well, I mean, okay, sorry, let me come back. So you have these 8 strings, but whatever number, I mean, whatever fraction you will see, I mean, this will be a very discontinuous number. And just notice that you have the 2 last strings have these numbers. So one has a length 11, the other has length 5, and you also have these parities. I'll come back to the 2 last strings in a few.
I'm not quite, so how do you see 11 and 5 from this side? What's 11 and 5 related?
So 11 is 1 plus 4. Oh la la. So no, that's yes, there are 8 strings. And this, okay, so this is more complicated to understand. So I wanted to explain that there are 8 strings, so this you can understand. So 11 and 5 is a little more difficult to understand. But the only thing you have to remember is that 11 plus 5 is equal to 16, and 16 is the denominator of this fraction. Just, I mean, this will clarify a little later. So 11 plus 5 equals 16. Just for the moment, that's the only thing. Well, I mean, so this is just to tell you that this is Takahashi business. I mean, I don't know if Andreas is here, but okay, it's quite complicated, and he doesn't like it. But okay, you're here. Okay, so he has a maybe we should come back. So now, is there a connection between? So I gave some kind of physical motivation and another one which was mathematical. But can we connect them together? So one thing I also did not indicate that there is a parameter also which did not completely appear clearly in the Hamiltonian, which is called the twist. So you can put a twist in your chain, and in fact, the degeneracies I talked about, they only occur at very special twists, which are called commensurate twists. So this is the twist, if you want. This is what q to the power L is just plus or minus 1. So you get plus or minus 1 to the power n times the twist to the power L. L is the denominator of the fraction, should be equal to 1. And that's a bit that's a bit strange. So what Jan did, he did some simple numerics. Actually, it's not very difficult. But if you move slightly away from these values, what happens? So you lose your exact strings. Well, it will always decompose into 2 strings. That's kind of an observation. And these 2 strings are exactly the 2 last strings of the Takahashi decomposition. So somehow, these complete strings, they are kind of made of bound states of the 2 last strings of the Takahashi decomposition. And now, why are these 2 last strings important? So this also you saw in Bulat's talk. I mean, I don't ask you to understand too much what is this called the Y system, but if you look at the Y system. The equation for typical, so this J refers to the number of the string. So you get a kind of equation like that, and the 2 last strings, they occur just at the 2 last lines, and you see that they both only the 2 last strings maybe this was said in other talks. Maybe no, not Andreas, but Andreas knows it. Only the two last strings coupled to the twist. So somehow it seems that there is, I don't say I really understand it very well, but it seems that there is a kind of deep connection between these complete strings, then the two last strings, and then the fact that only if you want really to have a kind of physical interpretation of the strings, only the two last strings seem to carry some current.
Can I ask this question? What is new here? Because we started with V, so now you have a D and
Yes, because well, I mean, this kind of equations, they are represented by a kind of dn. So nu is n or whatever. I mean, it's just you just label the nodes of your. So that's the
what exactly context of
new in. Nu should be L, I think, but I hope. Maybe I'm wrong. I think it should be L. So now I come back more to our technical work on this spin chain. So I would like to tell you a few tricks which, I mean, they are known to experts in the general case. For Q, not a root of unity. I am absolutely sure that if Bajanov was in this room, he would already have addressed me and telling me that this is something he knows perfectly well. But maybe the little new thing I want to add is that something nice occurs at roots of unity. And well, what occurs at roots of unity is that all the construction involves only finite dimensional matrices. Usually, even for not a root of unity, you build a Q matrix, if you want, which has an infinite dimensional auxiliary space. But in the case of the root of unity, everybody has finite dimensional. And where does that comes from? So you just write your Lax operator, this kind of Sklianin Lax operator I wrote before. And you observe that it can be kind of written in terms of a simple product like that. And it involves two matrices, U and V. So in general, to obey the RLL relation, this U and V are 2 by 2 matrices which are completely arbitrary. But in my case, in order to have a kind of lowest state property, so in order for S minus to annihilate the ground state, they are not completely general. I have to impose some constraint on them, but it's a mild constraint. And well, I mean, here I just need the Weil algebra. So this relation, Wx equal Qxw. And then you know, I mean, so this is also something I stole from Baxter in one of his papers. It is a kind of, this Lax operator is kind of factorized into two pieces. But not quite factorized. I mean, so it's kind of half factorized. So you have to work a little more to factorize this. Yes, and well, I mean, here now I want to somehow I mean, it's important that my matrices with internal space they commute with each other. So I have to kind of discover a kind of new Young-Baxter relation now, not the one I showed before, because now I have to find some R matrix with two red lines, if you want. And this R matrix, well, I mean, I found it, but for example, people like Derkashov and other people, they worked a lot about such R matrix. But you kind of somehow, well, what I mean, my matrices, if you want, this is I had two matrices, A and B. So now I have four. If I have two Lax operators, I have four small matrices, which the first one depends on U and V, 1, U2, V2. So you have to somehow be a bit clever and exchange the indices independently. So your R matrix has a kind of actually factorized product, and you have actually this exchange the U indices. You have to find another one that exchange the V indexes. It's a little technical, but okay, it's a kind of nice work and nice thing to do. But what I wanted just to say now is that what you are guaranteed with that, so now my transfer matrix was depending on two sets of two matrices, which I call U and V, and I can exchange independently U and V. So somehow I have this kind of product, T of UV, T of U0, V0, can be rewritten as T of UV0, T of U 0V, a kind of product written in a different way. And I mean, the kind of miraculous things that happen is that actually it's not very hard to show that one of these can be thought as the Q matrix, Q of U, and the other one can be thought of the P matrix. So what are Q and P matrices? They're just, you write, I mean, it is well known since the time of Baxter that the Bethe equation can be written in terms of T, in a matrix form, if you want. TQ equal, so this is a number. T0 is a number, T0 Q plus T. And you have another matrix which obeys this. And actually, they are quite easily realized in that case. But I mean, anyone who has a small laptop, he can really do this and check that. You don't need much need. Well, here, I mean, there are two tricks to use when you want to do that. You have to use this kind of factorization, and also the fact that you can decompose this representation into two representations when you take when you take the spin to be half integer values. And with that, and with that you obtain a quantity. So since P and Q, they obey the same equations, you obtain a kind of Wronskian equation. So that's a kind of Wronskian equation. But the important point is that now this special factor which I had before turns out in factor. So somehow when you have a kind of magic twist, I don't know how commensurate twist, the Wronskian vanishes. So due to this vanishing of the Wronskian, you somehow, I mean, if it was a differential equation, second order differential equation, when the Wronskian vanishes, you get that the two solutions are proportional. In that case, they are not quite proportional. They have a kind of regular part, which is proportional, but then there is a singular part. What I'm called singular is that this singular part depends on not on u, but on u to the power L. So it's a polynomial in u to the power L. And you find, so that's how they differ. They just differ by polynomials in u to the power L. And in fact, I mean, maybe since I don't have much time, all the so-called Fabricius-McCoy strings, they are the roots of this polynomial, P and Q. So I mean, it's little different technique. So what I wanted just to say is that, well, you can introduce now, you can somehow specialize to SL0. Well, I mean, let me forget about that. I mean, the point is that you have this, you take just the product of these two special polynomial which occurs, and it's easy to see that you can also express it in terms of ordinary roots. So it has two expressions. This is it has this expression, and so this is a polynomial, although it looks to have a kind of denominator. And the roots of this, so this is the kind of spin zero representation transfer matrix. So this is a number, it's not a matrix. And the roots of this polynomial, so this y of u is what is called the Fabricius-McCoy polynomial. And this is what explains the degeneracy about the special degeneracy of the Hamiltonian. So in a way, if you want these special roots, these Fabricius-McCoy strings, they have maybe not much role in understanding the spectrum of the T matrix, but they have an important role because they really explain the spectrum of the P and Q matrix. And so that's the message somehow, that if you want, if the physics is more contained in the P and Q operators than it is in the strings. So that's, oh yes, and maybe what is different from what you see Fabricius and McCoy, they considered the Q matrix of Baxter, and they were letting this parameter go to 1, so they were looking at the center of the strings, and the center of the FM strings, they didn't seem to have many, they couldn't really understand where it was coming from. But the construction which we do here, it's a kind of very special Q matrix. It's only working at the root of unity, and then its roots are this Fabricius-McCoy string. So okay, I think, well, okay, happy happy birthday, Hubert. I think it was, thank you very much for inviting me. And so this was a nice picture taken in Cargèse. I hope we will have opportunity to come back to Cargèse together sometime. And also I wanted to actually to wish a happy birthday to Jesper, who, I mean, actually I should have taken a picture from Les Ouches because we also had a great time in Les Ouches with you, Jesper, I remember. So maybe let's try to meet somewhere nice sometime, and thank you very much.
Okay, thank you very much, Vincent. Do we have some questions? So I have one question. You mentioned this Drude weight fractal.
Yes.
Rootability. Is it really a fractal, or it looks like a fractal, or is it really a fractal?
That's a nasty question because
Yes.
it depends. I mean, for this moment, I don't think there is any experimental measurement of this root weight at this special root of
No,
unity.
but on the mathematical level, can you?
No,
prove
I
it in
think
the fractal?
well, I mean, this is just a lower bound, so you could always
Oh,
say maybe. But you see, there is. I mean, there are other ways maybe to compute these root weights, which have been used by other people. So maybe I believe it's a fractal.
Okay.
But okay, you could.
Okay, now just one question.
So yeah, just maybe a comment about that. So since you know, I mean, with the developments on generalized hydrodynamics, so I mean, there have been many other quantities that have shown up that show the same, display the same fractal behavior. Right? So it's just because, I mean, in the end, it's just that the long time behavior depends very
Finally,
really depends on delta in a non-continuous way. So you get plenty of quantities that depend on just the denominator of the fraction p over q, right? And
they just don't just depend on the denominator. I think they depend on the whole fraction. But I mean, if I showed the
it depends what you include. So I had also a question about that. So one problem that I know where you also see that only the two last strings contribute is when you solve you want to compute the magnetization profile in the XXZ chain after a quench from the domain wall case, so from the domain wall state, so a state where all the spins are up on the left, all the spins are down on the right. So it's the same kind of result.
I think it should be close to.
So
I mean, it ultimately comes to the point that the flux, what I call the flux, only in the Takahashi equation, only Takahashi. I mean, in the beta equations, only coupled to the last two strings. So that's probably the reason why only these two.
Okay.
Often the equations are couple everything together, but at the
I mean, the statement that only the last two functions or the last two strings matter physically, I mean, it's a little bit deceiving because you have to solve for all nonlinear integral equations which are coupled, and then you take the last two functions, insert it into some integral, and then you get your physical result, but you cannot really kick out the rest. Yeah. It's still there.
I mean, yes. I mean, but I am more thinking as a physicist. I mean, suppose these strings really correspond to some kind of particles, in quote unquote. So it seems that many particles are neutral, and then that you would have two special particles that would carry some charge.
But it would only make physical sense if you could integrate out all the rest.
Yes. Well, maybe that's what you do. I mean, your techniques is probably doing this. I guess. So you only get two densities, and probably, yeah. I mean, that's what you explained me. So I'm not, I'm not discovering something really new. But that would be certainly an interesting way to obtain this. quantities.
Okay, so I think we thank you again, Vincent. Thank you very much.